Okay, so the second condition of equilibrium is that the sum of the torques acting on an object calculated about any axis is 0. And that means rotational equilibrium. So translational equilibrium was, left to right. This means, rotational, that all the torques balance out, so it's not rotating. When solving static problems, we'll first draw a complete picture, look at the free body diagram of each object in question, and then choose a convenient coordinate system. And we'll look at how there's certain axes that are going to be helpful for us, and we'll do that. Complete the sum of the forces, x and y, and they'll equal 0. And then the sum of the torques will add up to be 0 as well. So a box is resting on a beam with two supports at each end, and we have a box that's 3/5 of the way down from the end of the beam, and we want to find the support forces. So let's go ahead and draw this out. We'll have the beam on the two supports. We have the mass that's 3/5 of the way down from the end of the beam, and we can draw the forces there. So we have the force of gravity of the beam, we have the force of the box, and then we have the two supports, which is FA and FB, and we're just choosing A on the left, B on the right. Those are interchangeable. It doesn't matter as long as we keep it to the very end in terms of those variables. And we're going to set up the torques. So when we can choose a rotation point, we'll go ahead and choose this as our rotation point. We could choose it over here at FB, and that would have been okay as well. But we'd either want it here or here, because what will happen is when we look at the torques, we want to eliminate the factor of one of these variables, FA or FB, because both are unknown. We don't know either of them. So let's set up the sum of the forces in the y. So we have the positive, there's no forces in the x, right? The force in the y, positive FA plus positive FB plus negative force of gravity of the box plus negative force of gravity of the beam equals 0. So that's one equation that we can use. And the x, again, there's nothing that we can use there. And then when we set up the torques, and if this is a rotation point, the beam itself is going to cause a clockwise torque. So we have the negative torque of the beam plus, if it's, again, this is a rotation point, the box would cause along this lever a clockwise torque. So negative torque for the box. And then the FB would cause a counterclockwise torque, so positive torque from FB. And they're in equilibrium, so all the torques added up will be 0. So once we have that set, we're going to have to think about the setup in terms of the lengths, right? All we're given here is that it's 3/5 of the way down, this box. And we know that the beam is halfway down the beam, right? And then FB is the full length of the beam. So when we set this up, we can set this up in terms of those variables. FB is the full length of the beam, L, if this is L, the length of the beam here. And then the box is 3/5 L, 3/5 the length of the beam. And then the force of gravity of the beam is located half the length of the beam. So we can have it in terms of L. Once we do that, we can divide both sides by L. And we can figure out what FB is. So this is what the support of FB will have to hold, 1009.4. So if we think about it, the box is closer to FB, right? So because it's closer, it's going to have to support more. So we know that once we place this into here and figure out what's going on with FA, we know FA is, it's going to be less than FB. And so we'll place that in there, and we get for FA 882. So the force on the beam on the left is less than on the right because the box is closer to the one on the right, has to support more. All right, so let's take a look at this one. We have a bridge with two cars on it, and we want to figure out what do the supports need to be if we had, two cars like this on a bridge. We have mass 1 here as 1,700 kilograms, mass 2 is 1,900 kilograms. The mass of the bridge is 35,000 kilograms. And if we draw the forces, let's go ahead and be in the same conventions here. We'll call FA on the left there, force of gravity of the bridge, in the middle FG1 there, and FG2, and then force of the beam. The length of the bridge is 15 meters, and M1 to FA is 9 meters, and then M2 to FA is 12 meters. And we want to find out what FA is and FB. So I'm going to have you try this one. Set up the sum of the forces in the X, Y, and the sum of the torques, and set it all up in variable form like we did before, and see if you can solve for FA and FB. And when you're ready, you can check. So go ahead and hit pause, and then when you're ready, you can hit play to continue. Okay. So in the X, there's no forces. F1 in the Y direction, we have the positive FA plus the positive FB plus the negative force of gravity of the bridge plus the negative force of gravity of car 1 and car 2, and then the torques, the bridge, the force of gravity 1 and force of gravity 2 are all negative torques clockwise, and then we have the beam here, or FB of the beam is going to be the only positive torque, and that'll all add up to be 0. When we put the variables in there, FB is 15 meters from FA, and FG1 is 9 meters from the hinge point, and then FG2 is 12 from there, and then the force of gravity of the bridge, 7.5. You could have set up the hinge point here on the right hand side, and then the distances would have been different, the torque directions would have been opposite, and that would have been fine as well. So we place those in there, and we should end up getting 196,392 newtons for FB. When we place that in there, we'll end up getting 181,888 newtons for FA. And so it should make sense that FB, again, is supporting more of the whole load there because the cars are closer to it. And so that should make sense. And that's good there. So if we look at this scaffolding, it's being held from the top there. And when we think about scaffolding and the structure supports that are there, it's important to consider all those factors. So let's consider this one here. Let's say we have a person standing on the scaffold, and they're 3/4 from the end there. We've got the mass of them, we've got the mass of the beam, and we want to find the support structure. So we want to find out what is FA, what is FB. So we treat this one actually just the same way. We choose a rotation point, and we set up our forces in the X and Y. So in the X, there's no forces. In the Y, we've got the positive FA plus the positive FB plus the negative force of gravity of the beam, negative force of gravity of the man. Go ahead and set up your torques and see if you can solve for your one of your forces, and then use the forces in the Y to find the other one. So go ahead and pause the clip, and when you're ready to check, you can hit play to continue. Okay, so if you chose the hinge point here, your torques would be based on this. The beam as well as the man cause a clockwise torque. The force FB over here causes a counterclockwise torque. FB, we've got X, the full length there, the beam is half of the way, and then the man is 3/4 of the way. You could use L if you wanted to, but if you kept it in terms of X, you'd have that. You cancel X from both sides. And FB is 1,298.5 newtons. And once we know that, we can find what FA is, 906.5 newtons. So we treat these just the same way, and we can set up our torques and the forces and figure out what's going on.